Well, I'm still intrigued this morning. You're getting a double whammy on uh, heterosis, the idea. Um, More musings on it for this morning. Because now, uh, in our last video, having to do with ligers and heterosis as a means for gigantism within a hybridized species, and making certain assumptions about um, just the rapidity at which the gigantism could occur, making assumptions that just to review, that the liger, which is the largest cat presently, is about 1,000 pounds, which in one generation is double the size of its largest parent, approximately. All right, we're not gonna fuss over some of the, uh, the calculations, but we're gonna just ballpark it now and just see if it's just too ridiculous. Whatever. But anyway, all right. So with that working premise, then if we could get a liger and another liger that could have the same genetic situation as to double, because the liger females can be fertile. So then some other animal that would be able to breed with that one would produce a 2,000 pound animal in the next generation, and so forth. If we have a setup where we could, you know, again, this is all semi theoretical but falsifiable if you really wanted to go out, I guess, around and try to do this hybrid experiment. Um, so I just wanted to look up some of the things that we have access to Wikipedia and such. The smallest sauropod. Now these are the dinosaurs that the long neck, typical Brontosaurus, Diplodocus, Brachiosaurus, all that group. The real big ones, there's this dinosaur that I looked up, which was the smallest adult one, was Magyrosaurus. If I'm saying it, Magyaro saurus. Um, it was came in at about 1,000 pounds, right? And then to the biggest one that we found, I'm going to pick Giraffatitan, which was formerly known as Brachiosaurus. Uh, he's real big. He comes in at top estimates of 132,000 pounds, right? So 132,000. Right now, regressionally or projectively, I guess, looking at going from the 1,000 pound smallest sauropod to Giraffatitan, right, gives you only seven generations have to pass with that process of heterosis. You go from 1,000 to 2,000 the first, second is 4,000, 8,000, 16,000, 32,000, 64,000 in the sixth generation, 128,000 by the seventh, right? So now looking at that, if we were to, again, I looked up a paper that had all kinds of looking at the bone growth of these animals, and I guess they look at the, the canals and the laminations of the femurs, etc., to try to come up with age to adult size as well as age to sexual maturity. And interestingly, while there was some variation in the 25-year-olds, maybe 30, or um, you know actually it was like more like 25 and then less. There was some that was maybe 20. But nonetheless, I picked 30 as the top size, just to push it, just to see where the number would lead us. And then so if you look at each of those generations in a perfect system, obviously, which would probably, it never actually happens. You get generation 30, 60, 90, 120, all the way to 210 by generation 7. So it's 210 years. You can have 7 generations of heterosis, getting you an animal that's the size of the top animal. So only in 210 years, right? Um, so, uh, do we accept that in a specific way that you could have, just an acceleration? That's really all we're looking. I mean, I'm looking for from the standpoint of paracatafungogenesis is that while I don't propose a young Earth, of the 6,000 year variety, like certain individuals insist that the scriptures point that out. Neither am I an old earther. So, if you want to stretch the number of generations necessary to get this particular thing accomplished, that's, even if it was 400 years, that's still like pretty brief. Even if it was 4,000 years, that's still pretty brief, right? So all of these things, as far as like fitting into a construct of the creative days, um, not that we have it hammered down exactly how long each creative day was, because all 7 creative days are summed up as a day in itself. So there's kind of this scale. Um, uh, it could lead potentially to sort of a uh, moderately long, oldish Earth. Um, so anyway, uh, so that's my musings for that. The what was it? Was another point that I wanted to? Oh, was just with paracatafungogenesis, food is also an important aspect of it. So whatever they're eating also contributes to their, the symbiotes that these animals have in their guts. Uh, in the last video, I talked about my favorite, the deep sea vent worms. Get gigantism due to that. If there's the fungo part of paracatafungogenesis is the funguses, and um, fossil evidence for very large mushrooms growing at the time, changing their diet, uh, and the fact that we don't actually know which of these animals that somehow or other not connected or they are connected. We just infer that they've been speciated where they can't hybridize or whatever like that. So there you have it for this second burst of of interest in the word heterosis, which again is when a hybrid, you have an animal that hybridize that are supposedly reasonably closely related, that you get this extraordinary robustness in their size. Uh, it's done a lot with corns and plants and things like that. And applying it to mammals and their sizes. That's what we've been discussing. And then also too, well, you have the reverse, which is the diminishing. The animals that go the opposite way, where they die and there's nothing really special about them after that. They get all kinds of problems, perhaps, but you don't necessarily get all kinds of problems all the time. So you get these other ones that are super robust, like the ligers and so forth. Um, and people have argued, well, that's an aberration. Well, yeah, well, most of uh, the things that happen, unique circumstances can mess things around pretty good, and again, it's just a fun extrapolation on this, I thought. Anyway, so there you have it for this. I'm going to stop this morning. I don't think I'm going to think about this anymore. All right.